Astronomer Research Endowment Award 2000 and Sir J.C. Bode Award 2000 by IETE India. He visited the Birmingham University under Commonwealth Fellowship 1999. Hello. He has published over 200 research papers with recent citation of 2242, I-10 index of 47, and H index of 24. A senior member of the IEEE, he has past chairman of the IEEE AP's MTT chapter of Kolkata section during 2012-13, and the chapter received Outstanding Chapter for 2012 by the IEEE MTT Society and Best Chapter for 2013 by the IEEE AP Society. He has organized workshops, tutorials around the world, including Colorado, Paris, and Kuala Lumpur. Over to you, sir. You can proceed with your presentation.
Thank you, Dr. Behra, for a nice introduction. Good afternoon to all. And my thanks to Dr. Satyanarayan Sahu for giving me this opportunity to interact with uh, the participants in this FDP. Let me spend 1 minute or half a minute on the title. I could have given the title Mathematics from History, but I choose to say Ganita from Itihasa. Many people in India now, particularly in my age and those who are older to me, they differentiate Ganita from mathematics. Ganita is practical. Ganana, from Ganana comes the Ganita. Ganana is computation or calculation. So when it involves calculation, mathematical calculations using numbers, that is Ganita. Mathematics is different. Mathematics mostly takes some axiom, then they prove something. Everything is required a logical proof. Ganita does not require that. So Ganita has a proof, but it is not the Greek-based proof. So that is why in India we call it Ganita. Ancient India or ancient Bharatvarsh we call it Ganita. Itihasa instead of history, Itihasa means Iti ho aso. That is Itihasa, which means how it happened. So it is different from history. That the history recording now, what is being done, Itihasa is different. It describes it as a story. Everything is described as a story. And as the story goes on, how it has happened, that way it describes it. It includes some story, but it includes the facts. The facts are in terms of a story. So in India, we have two Itihasa. One is Ramayana, other is Mahabharata. And our Itihasa, the Bharatiya Itihasa, is rich with astronomy. Astronomy requires mathematics. Therefore, it is rich with mathematics or Ganita. So, we are going to see in this lecture Ganita as it was used in astronomy and as it is being used in physical sciences. What is physical science without mathematics? So today physical science as it is using Ganita, that we will see and we will see where its root lies. That is the purpose of this talk. What is the root? From where we have got these calculations or methods, etc., that we are using in today's physical science. So with this brief on the title of this lecture, Let us start. In Bharatavarsha, mathematics had application in different domains. For example, mathematics was used or Ganita was used for counting, enumeration. For example, we used numerals, we used arithmetic as evident in Rig Veda. Rig Veda uses numbers, it describes powers of 10. Then in Rig Veda also, as a part of Vedanga Jyotisha, we have Jyotisha. Since we have Jyotisha, we are using numbers and different calculations like geometry, etc. Also, we used modeling particularly for astronomy, astronomical modeling. They require trigonometry, approximation, equation solving. These are dealt with in Surya Siddhanta and by Aryabhatta in Aryabhata. Then we were a very prosperous country. Prosperity comes from commerce. As we have a saying in India, Vanijya Vasati Lakshmi. So prosperity comes from commerce. We were very rich. We had a very rich commerce tradition. Commerce requires arithmetic, algebra, solving equation, etc. So these are evident in Arthashastra of Kautilya, and we will see Bakshali manuscript. We will not see it in detail today, but and there is something called Bakshali manuscript that we will see. Then we had architecture, like you see temples, ancient temples, they require architectures. They require architecture means it requires geometry, right angle triangle in geometry, circle, pi, square root, etc. These are available in Sulva Sutra. We'll see Sulva Sutra now. Just after this slide, we'll go to Sulva Sutra. Then we had some advanced modeling for approximations of function, polynomial series, infinity series, calculus, combinatorics, discrete mathematics, etc. These are given by different rishis like Pingala, Madhava in Itihasa, also later by Ramanujam and Newton, Leibniz. This I will skip later. Okay. Now let us go to the next one. As how we discussed, we are going to discuss about Sulba Sutra. Now it has a term Sutra. What is Sutra? Sutra has a definition. The definition is given above in the Sanskrit. Let me translate it. Instead of reading it out, let me translate it word by word. The first word is Swalpakhyam, which means minimum number of alphabets. Asandidhyam, which means unambiguous. It should not be ambiguous. The sutra should contain minimum number of alphabets. It should be unambiguous. There should not be any ambiguity in it. Sarabadha, which means concise. It should be very concise. Vishwatamukham, which means universal. So sutra should be applicable everywhere without any restriction. It should be applicable everywhere. Everywhere it must hold good. Astobhang means non-redundant. So non-repetition. Whatever you are putting in the shloka, it should not be repeated. Non-redundant. Anavadiyamacha. Without a flaw, it should not contain any flaw. It should be correct. Sutram sutra vido vidu, which means this is called a sutra. So a sutra contains minimum alphabets, is unambiguous, is concise, is valid universally, has no redundancy, and is without a flaw. Such a sutra is a Sulba Sutra, which is applied geometry. So we are going to, so now remember one thing. When you say sutra, it is given in the form of a sutra, means we are not looking at the proof of the sutra. What is the sutra? Sutra. Why you use sutra? Because you can readily use it. Immediately you can use it. You don't require to go through the proof it, then use it. That is not required. Straightly use it. One such sutra that we all are aware of if we are reading science is the Pythagoras theorem. Pythagoras theorem says a square plus b square is equal to x square, or p square plus b square is equal to x square. That is what is Pythagoras theorem. So instead of remembering the proof, if you remember Pythagoras theorem, you can use it wherever you are dealing with a right angle triangle. Now this Sulba Sutra has contribution from different rishis. Baudhayana, Apastamba to Varaha. Baudhayana Sulba Sutra is perhaps the oldest Sulba Sutra. It has 3 chapters with 520 sutras. We are going to see one of the sutras from Baudhayana Sulba Sutra. Next. As I told, the one sutra is Pythagoras theorem. Base square plus side square is equal to hypotenuse square. And we know from the school days, when we studied science and mathematics, that Pythagoras gave this theorem. Who was Pythagoras? He was a Greek philosopher of 500 BCE. But Pythagoras never gave this. This was given by one of his students, one of his followers. These followers were called Pythagoreans. Therefore, nowadays it is called Pythagorean theorem. The theorem was given by Euclid, who came 200 years after Pythagoras and who documented the theorem. Okay, this remember it is 500 BC. Pythagoras time is 500 BC. 200 years after it is documented by Euclid, which means around 300 BCE, before the current era or before the Christ era. Next. Now look at this Baudhayana Sulba Sutra, one sutra from the Baudhayana Sulba Sutra. Baudhayana Sulba Sutra is conservatively dated as 800 to 400 BC, between this period. So this predates the Pythagorean period or the Euclid period. So this sutra existed before Pythagoras or Euclid and in Bharatvarsh. What does this mean? It means this sloka means if we consider a rectangle and take a rope, stretch it along the length of the diagonal of the rectangle, then that will produce something which the vertical and horizontal sides of the rectangle produce together. So this something, let us take it to be area, although it is not mentioned here area, many people contest it, it does not say area. If it is area, then p square plus b square is equal to x square. Because each side, both this diagonal, its square will be the area of a square whose side is the diagonal. P is the that p square will be the area of a square whose side is p. Similarly for b. So this gives this. Now, if we say that it is not area, area was prevalent in those days in the society. Therefore, area is not mentioned. It is kept what is called viha. So it is kept a secret, not a secret, it is kept aside because it is understandable. Anyway, let us see the next sutra, the very next sutra of the Baudhayana Sulba Sutra. The very next sutra says if you have two different squares of different size and want to merge them into one square. So from two different squares, you want to get one square whose area is same as the area of these two different squares. Then what you will do is you can outline a rectangle within the larger square using the side length of the smaller square as its width of the rectangle which is within the larger square. Then the diagonal of this rectangular section will be the side of the length of the combined square. So figure 1 shows you two squares. The red is the larger square, purple is a smaller square. Then inside the red, we have drawn a rectangle, purple rectangle, whose one side, the smaller side, is the same as the side of the smaller square or the purple square. Then we take the diagonal of that rectangle, this perpendicular, this purple rectangle, the diagonal, the dashed line, which is in the figure 3, the dashed line, that is the side of the square which whose area is same as the area of the larger square plus smaller square. This we can now prove easily. What is the proof? For the larger square, area is suppose a square. Smaller square, area is suppose b square. And then what is the area of the combined square? It is a square plus b square. Now look at this figure in the figure. For the purple rectangle, one side is a, other side is b. Therefore, its diagonal is a square plus b square. Because the diagonal, if the diagonal gives you the area of the combined square, then diagonal should be a square plus b square. So in the previous row, it meant this square. Okay, these two are saying us that we had this Pythagoras theorem earlier in Bharatvarsh. Next. Then in the Manava Sutra, we have a clear definition of the Pythagoras theorem, which is h is equal to square root of p square plus b square. Now look at this square root. It is very important. Why? Because in those days, early days, they were using Roman numerals or something which is akin to Roman numerals. They were not using the decimal system in the West. Now, in the Roman numeral, there is no provision of finding a square root. Using Roman numeral, one cannot find out the square root. So this is purely indigenous. Next. Then we will see one of the treasures of ancient Bharata. This is called Boxari manuscript. This was found near Peshawar in Pakistan of the modern days in 1881 current era by a farmer while he was plowing his field. Now this contains a mathematical compendium of 70 files and now it is available at the Bodleian Library in the Oxford. This is a Bitbark manuscript. It contains Gatha dialect of Prakriti and the script is Sarada script. It has been dated. Date 36, folio 16 is 224 to 383 CE. Other folios are later. Next. This picture shows us the earliest zero inscription. This is in the Chaturbhuja temple in the Gwalior. If you go to Gwalior, look at the go visit Chaturbhuja temple. On its walls, this inscription you will find 270. This inscription is in the ancient Nagari script. And there you can see 0. 270. 0 you can see the modern 0 you can see. And this is accepted as the earliest inscription by both people who support West and people who does not support West or people who are Indic those who say that it has come from India, and others also. Now, why this is important? Because you look at it, 875 CE. This is dated to be 875 CE, which actually supports the Aryan invasion theory. That is, Aryans came to India, they invaded India, and India got knowledge from them. Then they invented zero. In India, people invented zero. So this 875 CE is after the Aryan invasion. And that is the importance of this. Others are available in copper. There is inscription, but people say that those are plagiarized or those are manufactured. You can take a copper plate of maybe 200 BCE, then today you can inscribe something. So inscribe the zero and say that it is of 200 BCE. So that is why that is discarded by many people. But this one is not discarded. Now beyond this, so 875 CE is the zeros inscription. So after 875, zero came to India. Next. Now look at this Baksali manuscript. A page from the Baksali manuscript. It shows a bold dot. The bold dot is the oldest record of zero. So in those days, when this Baksali manuscript around 200 200 CE, in the Baksali manuscript, bold dot gives you the zero. So zero was available in India much before the Chaturbhuja temple inscription. Next. In the Baksali manuscript, there is an interesting thing. Finding out the square root of a non-square number. Suppose R is a non-square number, then divide it into two parts. N square, n is a perfect number, which is the highest number whose square is within R, then plus the remainder small r. Then in the Baksai manuscript, there are three approximations. Zeroth approximation is root over of R is approximately equal to n. First order approximation is root over of R is approximately equal to n plus r by 2n. Second approximation is root over of R is approximately equal to n plus r by 2n minus r by 2n whole square by 2 n plus r by 2n. Its application is given below. Root 5 using this second approximation, you can find it correct up to 4 decimal points, 2.2361. The right side, let us forget it. These are the error calculation and proof. Next. Now look at this. You know, in science, mostly if you are using physics, mathematics, or even chemistry, engineering, technology, we are conversant with something called Newton-Raphson formula, which is xi plus 1 is equal to xi minus fxi by f dash xi. That is, if fx is a function and you want to find the root of the function, this is the formula. Use it. Now let us take x square is equal to n square plus r and fx to be x square minus n square minus r. So zeroth approximation, let us take x is equal to x0, that is n. We start with zeroth approximation. First correction is I is equal to 0. So if I put I is equal to 0, then x1 is equal to x0 minus fx0 by f dash x0, and that is equal to n minus of minus r by 2n, which is n plus r by 2n. This is the first approximation in Boxali manuscript. Second correction, I is equal to 1, x2 is equal to x1 minus fx1 by f dash x1, that is n plus r by 2n minus this number, and if you simplify this, that becomes the right hand side, which is the Boxali formula. Second correction is the Boxali formula. Now, please think, in the Boxali manuscript, they are using this formula. Did they know Newton's Raphson method, how they arrived at this formula? To arrive at this formula, you have to know something like this. So they use something to arrive at this formula, which is equivalent to Newton-Raphson formula, which we today call Newton-Raphson formula. They might have used something which is like this. This requires tremendous amount of calculus, which means they might be aware of calculus. I'm not saying that they are aware of calculus, but they have to use something like this to arrive at this formula. Next. Then linear programming is very important in physical science, business administration, etc. This started after this World War II because US military sought to move men and material using minimum cost. George Dantes, he invented the simplex method for solving LP, and it takes very large time. The original simplex method requires huge amount of time. Narendra Karmakar at AT&T Bell Lab, he developed an algorithm named after him, which um, accelerated the calculation. So he is listed as a highly cited researcher by Institute of Scientific Information. So this is one contribution from India to linear programming. Next. Now look at this problem. Electronics. Let us say it can be any discipline from electronics, let us say. One student possesses 7 registers. Each register cost is x1. Another 9 capacitor cost is x2. Another student contains 10 inductors cost is x3. Each give two components to one to each of the others. Then the total price of the components with each student becomes equal, which is k. So the price of the components with student 1 is k, price of the component with student 2 is k, and that way. Now the question is find the price of each component and the total value of the components possessed by each student. Alright. Now what you will do? This, let us put it in this form. Initial formulation is first student has x1 has 7 components with x1 price. So 7 into x1 plus x2 he has nothing, so 0 into x2, x3 which means the third register inductor he has nothing, 0 into x3 minus k1. Suppose the price of 7x1 is k1, so 7 into x1 is k1 and that is equal to 0. Similarly for the second student, for the third student. Now after they exchange the components, this equation becomes this. Now 5x1 plus x2 plus x3, where from x2 comes because second student gives one component to the first student. Where from x3 comes now, third student gives one exponent component to first student. Why 7 becomes 5? Because he has given away two components, one to second student, one to third student. So this way you formulate this equation. Now the purpose is to solve this equation. This is a linear programming problem. We will see exactly similar problem in Boxer manuscript. One person possesses 7 ashwars, another 9 horses, and another 10 camels. Each gives 2 animals, one to each of the others. They are then equally well off. Find the price of each animal and the total value of the animals possessed by each person. This is a problem from the Boxali manuscript. And you can now put this problem in this form, equation form. 5x1 plus x2 plus x3 minus k is equal to 0, etc. These three equations. This is perhaps the first LP problem of the world. What you have to do is find out or maximize CTT is transpose. Transpose of C into X is to be maximized such that AX is equal to B. What does this mean in terms of this equation? Maximize 5 on 1 transpose into X such that 4x1 minus 6x0 is equal to 0. 4x1 minus 7x3 is equal to 0. How do you get these two equations? 4x1 minus 6x2 is equal to 0. Equation 1 minus equation 2. Similarly, equation 1 minus equation 3 gives you the second equation. Here, the constraint is x1, x2, x3 are all integers. If you solve it, next. The Buxari manuscript solves it to give uh, k is equal to 262, which gives x1 is equal to 42, x2 is equal to 28, and x3 is equal to 24. Actually, this can be, for the smallest value, it can be, k can be 131, x1 will be 21, x2 will be 14, x3 will be 12. We can have many values like this. And this is what they solved using this. So this is the solution in the Boxer manuscript. First LP problem, linear programming problem, was solved in Bharatavarsha. It was posed and solved. Next. Then let us see some problems from different disciplines of physical science. From electronic discipline, we have two devices. They emit signals at intervals A is equal to 4 millisecond, B is equal to 6 millisecond. Their initial offsets are Ra is equal to 1 millisecond, Rb is equal to 2 millisecond. Determine the smallest time n when the signals align again. How to formulate this problem for solution? You have to formulate this problem. Formulation will be n is equal to 4x plus 1, that is equal to 6y plus 2. Solve for n, x and y, which are integers. Next. Exactly similar problem in astronomy. Two planets orbit a star with period A is equal to 365 days and B is equal to 687 days. Their initial phase offsets are Ra is equal to 10, Rb is equal to 20. Find n, the time in days when the planets align again. This is an astronomical problem. Formulate it as n is equal to 365x plus 10 is equal to 687y plus 20. Here is a problem from physics. Two wave sources have frequencies A is equal to 5 Hz, B is equal to 7 Hz. Initial phase offsets are Ra is equal to 1 second, Rb is equal to 3 seconds. Find n, the time when they align again. Formulation is again same, n is equal to 5x plus 1 is equal to 7y plus 3. Problem from chemistry. Two processes in a reaction, chemical reaction, cycle in a chemical reaction cycle occur every 12 minutes or 15 minutes with initial offsets of 3 minutes and 4 minutes. Find the time n when both processes align. Again, put it as n is equal to 12x plus 3 is equal to 15y plus 4. If you look at this, what is this? What we are going to do? We have to solve an indeterminate equation of a first degree, which is n is equal to ax plus ra is equal to by plus rb. This is the equation. In all those cases, this is the form of the equation that is to be solved. All right. Now we'll see how it is to be solved. Next. This was given by uh, um, Brahmagupta. Brahmagupta gave this Shloka for solving the such a equation. The meaning is given in the right hand side. Instead of reading out the meaning and Shloka, I will show you how it is done with one example. Next. So now we have n is equal to 34x plus 2 is equal to 13y plus 10. Now, if you look here, A is equal to 34, B is equal to 13, RA is equal to 2, RB is equal to 10. So, RB is greater than RA, so RB is called Adhikagra. If RB is greater than RA, then B is called Adhikagra Chhed. Okay. Then RA minus RB minus RA is equal to 10 minus 2, that is equal to 8. The difference is 8. What we will do is 34 and 13 will take. and we'll divide 13 by 34. Why we will divide 13 by 34? Because B is Adhikagra, 13 is Adhikagra. So Adhikagra is to be divided by 34 by A. So 13 will be divided by 34. So quotient will be 0. If you take quotient 0, then the remainder is 13. 13 will now be divided by 34. Sorry, 34 will be divided by 13. So that will give you quotient 2 and remainder 8. Then 13 will be again divided by 8. Remainder 1, quotient 5. 8 will be divided by 5. Remainder 1, remainder 3, quotient 1. Then 5 is to be divided by 3. Remainder 2, quotient 1. Now look at the result. 2, 1, 1, 1. First result you will leave out. Then format table. In the table, write 2, 1, 1, 1 in the first column. Then write, find out what is the next row after the last one. 2, 1, 1, 1 are the results or the questions. So 2, 1, 1, 1, then t is equal to 2. From where you get t? The t we will find out by finding 2 into t plus 8. 8 is the difference between RA minus RB. If it is the number of quotients is given, then 2 into t plus 8. If the number of quotients is odd, then it is 2 into t minus 8. Now 2 into t plus 8 has to be divisible by 3. From where you get the 3? 3 is the remainder of the previous the penultimate reminder. Last reminder is 2, penalty reminder is 3. So from that we get 3. So 2 into 8 plus 3 is to be divisible by 3. So for that t has to be 2. If t becomes 2, it will be divisible. Now take t is equal to 2. So that gives you 2 into 3 plus 8 gives us 12. 12 by 3 is equal to 4. That will be the last. So form this table. Then the next column, take t is equal to 2, so that 2 will be taken to the right side. Last row will be left out. Then above 2 will be 4 plus 2, and that is 6. Then similarly 6 will be taken to the next row, next column, and above 6 will be 2 plus 6, that is 8. 8 will be taken to the next column. Above 8 will be 6 plus 8, that is 14. Now in the next column, 14 will remain as it is. 14 will be taken to the next column. Above that is 14 into 2 plus 8. 2 is in the top, that will be multiplied by 14. 28 plus 8, 36. So 36 and 12, 36 and 14 you get. Now divide 36 by 34. 34 is the coefficient A. So this 36 is to be divided by 34. That gives us remainder 2. Then find out n. N will be 2 into y. So 2 into 13 plus 10. That is 36. So 36 is the desired number. So this is how you solve this type of indeterminate equation. This was given by Brahmagupta much before the West gave the algorithm. Next. Now consider another problem. A job scheduler allocates tasks X and Y to two processors such that the total processing time is proportional to 3xy is equal to 2x plus 5 plus 7. Find X and Y for the allocation. This is a problem from computer science. Another problem from chemistry. In a reaction, X moles of reactant A combine with Y moles of reactant B. The reaction rate is given by 4 and Y such that this equation holds. This reaction rate equation holds. These types of problem in ancient Bharatvarsha was called the Bhabita problem. Next. In the Bhabita problem, we have an undeterminate equation with product. XY is the product. So AXY is equal to BX plus CY plus T. In this form of the problem, in this form of the equation, uh, we have to find out rational solutions to the equation. This Shloka gives you the algorithm. Algorithm I am describing below. Solution is choose any number, sto is P. This number is called sto P. To obtain the quotient Q, which is called of T, such that BC plus AD by P is equal to Q is equal to AX minus C. If you find out this, then X is equal to CQ by A or C plus P by A. Y is equal to B plus P by A or B plus Q by A. Let us look at an example. XY is equal to XY minus 3X minus 4Y is equal to 90, which means A is equal to 1, B is equal to 3, C is equal to 4, D is equal to 90. Write this in the form AX minus C into AY minus B is equal to AD plus BC. Now A is 1, so X minus 4 into Y minus 3, AX minus C into AY minus B. So that you get is equal to AD 90 into 1 plus BC, so plus 3 into 4, which is 90 plus 12. 90 plus 12, you can write it as 6 into 17. 90 plus 12 is 101. So that you can write as 6 into 17. So if you take that, then x minus 4 is equal to 6, y minus 3 is equal to 17. From that you get x is equal to 10, y is equal to 20. But this is not an unique solution because 102 we can write as 2 into 51. If you write that way, it will be x is equal to 6, y is equal to 54. Similarly, you can find other numbers. Because it is indeterminate equation, you cannot find a unique solution, but different solutions you can find. This is called the Bhavito problem. Next. Then there is something called a Bhavana problem. Let us consider two capacitors which are storing energy in proportion to x square and y square. Total energy difference is 2x square plus 4 is equal to y square. Find x and y. Similarly, another problem from physics. A vibrating string has energy levels proportional to x square and y square. The difference between the energy levels is 5x square plus 12 is equal to y square. Find x and y. These x and y are integers. Now, one problem from the astronomy. The orbital energies of two planets are proportional to x square and y square. The energy relationship is 3x square plus 10 is equal to y square. Find x and y. These three are same type of problem. Next. The problem is if n, x and y are integers, find solution to nx square plus z is equal to y square. If x1, y1 and y1, z1 and x2, y2, z2 is a solution to this equation, then so is x1, y1, x1, y2 plus x2, y1, uh, then nx1, x2 plus y1, y2 and z1, z2. So that will be the next solution. And continue this till you get the equation in the form nx square plus 1 is equal to y square. Let us look at one example, Brahmagupta's problem. Solve for 92x square plus 8 is equal to y square. Now, nearest square to 92 is 100. So let us take y square is equal to 100, which is 10 square. Then x square is equal to 1 because 92 plus 8 is equal to 100. So x square is equal to 1. So x, y and z are 1, 10 and 8. So that is the Bhavana, first triplet of Bhavana is 1, 10 and 8. Then the second triplet, x2, y2, z2 also let us take the same. There is no restriction in taking the same one twice. So 1, 10 and 8, and take it with 1, 10 and 8, find out x1, y2 plus x2, y1, etc. So those will be 20 plus 20, 192, 8 square. Let me explain it how you got it. 1 into 10 plus 10 into 1, that gives you 20, which is x1 y2 plus x2 y1. Then n is 92, so 92 into x1 x2, 92 into 1 into 1, 92 plus y2 into y1, 10 into 10, 100. 100 plus 92 is 192. Z into Z, 8 into 8 is 8 square. So from that you get 92 plus 20 square plus 8 square is equal to 192 square. Divide both sides by 8 square to get Z as 1. So that gives you 92 into 5 by 2 square plus 1 is equal to 24 square. 5 by 2 whole square is not integer. So again apply the Bhavana. So 5 by 2, 24, 1. And if you apply Bhavana once more, follow the same process, you will get 120, 1151 and 1 square. So 92 into 120 square plus 1 square is equal to 1150, 1 square. This gives you the solution because Z has become 1. So 120 square, X is 120 square and Y is 1, X is 120, Y is 1151. Next. So let me have a comparison with West and India. The indeterminate equation AY minus BX is equal to C was solved by Aryabhatta using Kuttaka principle in 499 CE. Then later by Bhaskara in 600 CE. Then by Mahavira 850 CE, etc. So latest was by Narayana Swami 1350 CE and others. In the West, it was solved by Bassett in 1621 CE. Okay. Second problem, dx square plus z is equal to y square or nx square plus 1 is equal to y square. This was solved by Brahmagupta. This was proposed and algorithm was given by Brahmagupta. We have just seen that in 628 C. Similar problem, exactly same problem was given by Bhaskara. Only difference is he took n to be 61, z to be 1. So 61 square plus 1 is equal to y square. He gave it as a challenge. Who can solve it within 1 month or 1 year? I don't remember exactly. He will be called a mathematician. That was the challenge by Bhaskara. He had the solution. Same problem, same numbers was given by Fermat in 1657. See, Bhaskara too gave it in 1150, but Fermat gave it in 1657. Exactly same problem for solution. Then the solution is smallest problem, smallest integer value for x and y are given in the bottom. And Euler later rediscovered the Bhavana identity in the 18th century. So India was much ahead, Bharata was much ahead, of course. The algorithms that we are using today in different names, Euler's names, or Fermat's name, etc., were actually proposed in India also. I don't say that they copied it from India. It would have come independently to them, but this was existing in India. What would have been Fermat's astonishment if some missionary just back from India had told him that each problem had been successfully tackled, thereby native mathematicians almost 6 centuries earlier, because 1150 and 1657, you see, about 600 years gap. So what would have been his astonishment? This was posed by AV. Next. Then why Ganita was important in India? Because it was important in Jyotisha. Jyotisha had geometry and other branches. Geometry includes calculation of radii of different planets, trigonometrical observations to calculate relative positions of planets, designs and manufacturing of certain astronomical equipments. Other branches include time rate of change of planetary motion, calculating ratio of planetary position, which require knowledge of calculus and knowledge of trigonometry. Let us see if some of them are available. There are, I will take some examples from Jyotish or astronomy. One is calculating the position of celestial bodies. What is the problem? Determine the angular position of sun, moon, or planets at a given time. The method used by Aryabhatta was finding by using sine and cosine functions. He calculated the projection of celestial bodies, circular orbits into sky. For example, the true position of a body can be found using trigonometric correction for elliptical motion because orbits are not exactly circle, they are ellipse. Aryabhatta used that, used sine and cosine, you will see that. Then determining ecliptic coordinates. Problem is convert a celestial body's position between ecliptic coordinate system and equatorial coordinate system. In for this also you require sine and cosine. Then predicting eclipses. Problem is compute when and where solar and lunar eclipses will occur. Aryabhatta again used trigonometric functions like sine, cosine, etc. To model the apparent sizes of sun and moon and their relative positions during an eclipse. For example, he models sin theta is equal to r by d. R is moon's radius, d is distance from earth. This way he did. So this required knowledge of trigonometry, at least knowledge of trigonometry. And calculus that we'll see later. Next. Now for trigonometry, forget this Shoko. Next. In this Shoko, they didn't know what is sine, what is cosine. They defined their own things. So take a circle. On the circle, consider these two radii. One is the green color, other is red color. Then on the right hand side, you consider a portion which is called chapa or arc and join the 2 points of the arc that gives you the jia, or in English we call it chord. So you have a chord, chord is they called jia, arc they called chapa, from the center to the or to the chord end is called corner. From the center up to the chord is called poggia. From the chord our midpoint up to the perimeter of the circle is called sol. So let us see it in next. Now if you look at this looks like a bow. In the bow, you put an arrow that is called sorrow. That is why this is called sorrow. They call this sorrow. And this one, this red one is called corno. The brick color one is called ja. Complete one is ja. Half of this is called half or the ja. But for practical purposes, they called it ja. The other ja is also used as ja. Then this koja. Now, if you look at this, what you can understand is look at the triangle, corner jia and koja. They form a triangle. Now, if corner is equal to 1, which means radius is equal to 1, then the theta angle between corner and koja, that theta is sine theta for that, sine theta is equal to jia. And for that, cosine theta is equal to cosine and sorrow is equal to 1 minus cosine. Next. Now let us look at the development of trigonometry in West and West. Hipparchus, 1550 BC, is called the father of trigonometry. What he did is he divided angles to steps. For each 124th step, he tabulated chord. Then came Ptolemy. He divided 180 degrees into 360 steps, computed chord length. Both of them computed chord lengths. Neither the tables of Hipparchus nor of that Ptolemy is surviving today. Then comes to India or Bharat. Surya Siddhanta. In Surya Siddhanta, the terminologies for different functions were different. The functions were used sine, cosine, and inverse sine. Sine was called jya, cosine was called kojya, utkramaja is called cosine, and utkramaja is called inverse sine. The sine or the jya in Sanskrit, when it went to Arab, in Persian it became jiva. So jya was jiva, then distorted to jiva. Then this jiva got a name synonym in Latin, which later became sine in English. Aryabhatta, he developed a trigonometric table for different sine values in 3.75 degree steps between 0 to 90. Bhaskara gave sine approximation, Brahmagupta gave an interpolation, Aryabhatta also gave interpolation that we'll see, Madhava gave infinity series. Next. Now look at this red box. In this Makhi, Vaki, Faki, etc. That if you look at this is not a Sanskrit shoko. It looks like a Sanskrit shoko, but it is not a Sanskrit shoko. It is numbers. These numbers are sign differences in terms of minutes of art. That was given by Aryabhatta using his alpha syllabic number system. Next. Since we are considering trigonometry, I am saying this. So that shoko is written here, and uh, how to decode that Maki, Vaki, etc. That is given in the above shoko. What you will do is consider the vowels or are as 10 to the power 0, E 10 to the power 2, etc. up to O. Now, if you use from Ka to Ma, then the upper line 10 to the power 0, 10 to the power 2, 10 to the power even numbers. If you use from 0 to Ha, 10 to the power odd numbers, 10 to the power 1, 10 to the power 3, etc. will be used for those vowels, for multiplication with those vowels. Then he assigned numbers Ka to Ma, Ka, Ma, Cha, Nya, Na. So those 5 into 5, those numbers were given 1 to 25. Then Ja to Ha, Ja is 30, Ra is 40, Ra is 50. That way Ha is 100. That he gave. And now let me give you one example, Makhi. Makhi is Ma plus Kha plus E. Ma is 25, Kha is 2, E is 100, but Kha and E are cojoined. Because He is Kha and E cojoined. So 2 into 100, that is 200. 200 plus 25 is 225, that is Makhi. Similarly, Vaki is 225, 224, Hakya is 131, etc. Other numbers you can find out easily next. Similar to that is called Kottapayadi system. This was from the southern part of India. There all the vowels are 0. Then Kottapaya is 1. That way you assign the numbers. This is a shloka and this is a shloka whose meaning is given on the right hand side. But if we use the Kottapayadi system, it gives you the value of pi given below in the red number. Next. Now let us look at finding the R sign using geometrical method. The chord of 1/6 circumference of a circle is equal to radius. This was given by Aryabhatta. Now look at the circle. In the circle, if you take a chord BG or BC, these are these chords are 1/6 of the circumference. Then the they are equal to BC. Chord is equal to the radius R. That is what he proposed next. So he said that first take a quadrant, then make the quadrant of the circumference of a circle be divided into many parts as per requirement. Then from the right triangles and rectangles, one can find as many arc signs of equal arcs as one likes for any given radius. That is it told. I'll show you next. And what he did is he took arcbits theta to be 90 by 24, which is 225 minutes or 3 degree 45 minutes. And he found arc sine I theta, and that is called to P I N I. Look at the bottom figure. So from P to the lower radius drop a perpendicular. That perpendicular is Pn. So P1 to the lower one N1 is P1 P1 N1. Similarly P2 N2 etc. Next. Now let us uh, consider how to find this. Next. Now R, capital R, what he did is he took the circumference by 2 pi is capital R. Circumference is 360 degrees. As you know, 2 pi R is circumference. Therefore, R is equal to circumference by 2 pi. So 360 by 2 pi, 360 into 60 minutes. 360 degrees, 360 into 60 minutes by 2 pi. That is approximately 3438. So R is 3438. So this shows that chord of 60 is equal to R, because chord of 60 is equal to 3. Chord of 60 is equal to 3 R that we have seen from the past slope, that is equal to 3438. Now consider the triangle OBC. Here, if you consider triangle OBC, BC is equal to R sin theta, that is equal to R by 2, which is equal to 1719. 3438 by 2 is 1719. Consider the rectangle OABC. In this, AB is equal to R sin 60, and that is equal to again OC. That is equal to OC is equal to root over of OB square minus BC square. That is equal to root over of OB is R square, BC is equal to R by 2, so R square by 4. That will give you R, you put 3438, that you will give you 2978. So from 30 degree, R sin 30, we got R sin 60. So 8 sin to 16th R sin we got. So if you know R sin theta, you can find out R sin 90 minus theta following this process. Next. Again consider angle CBD, a triangle CBD. BC is equal to R sin 30, CD is equal to OD minus OC here. That is R cos 30 versus 1 minus cos. So BD is equal to cot 30, that is equal to square root of R sin 30 square plus R cos sin 30 square. Why R sin 30 square? That is BC square. BC square plus CD square. This is R sin 30 square plus R cos 30 square. That will be, put the values, that will be 780. So BD we got. Now R sin 15 is equal to half BD, that is 890. Similarly, we can now find out R sin theta. If you know R sin theta and R cos sin theta, you can find R sin theta by 2. Similarly, in triangle ODE, you can find out sin R sin 75. This way, all the angles you can find out. Next. Now, let us come to differential equation that we use in physical science mostly. It contains two techniques: differential calculus or rate of change, and limit of the summation of limited series, which is integral. Next. Now the question is, who invented this calculus? Newton or Leibniz? Both are credited because there was a tussle, so both were credited. They were of the same time, around same time, both were credited. Next. Now consider this RLC circuit, oscillation circuit. Voltage model in RLC circuit is this. Anybody in physics or electronics knows this. L d square I by dt square plus R di by dt plus I by C is equal to Vt. If you discretize this, this will be L. Discretize means take the difference, central difference. So for d by dt, you take the central difference. If we taking the central difference, we get this equation, the bottom equation. Next. Now there is a problem. An RLC circuit with L is equal to 1 Henry, R is equal to 2 ohms, C is equal to 0.5 farad, has initial current I0 is equal to 0.1 ampere. The initial rate of change of current is di by dt is equal to 0. Compute currents for different times. Now what you will do is take the above equation, discrete equation, put Vn is equal to 0 and find out In plus 1 from that equation. So this gives us a, using second difference, In plus 1 is equal to 2In minus 1 plus del t square into this. Now, for in, we know what is I0. So from start, and then In minus 1 is same as I0. Put those values and get different I values. Why you use this? Because you can solve the first one, but you will get sign. But that is in the steady state. But in the transient state, you will get the values only using the difference equation. Next. This is another problem from physics. Pendulum, you give is described by d square theta by dt square plus g by L theta is equal to 0. Next. And this is the problem in pendulum. Pendulum length is given, angle is given, and at that angle it is relief. Find out the theta t for different t. It is same process, follow the same process, take the second difference and you get theta n plus 1. This is a recursive relation. This is what I mean to say is you don't require in practical situations, you don't require differences or integration. You actually practically differential equation is solved when you use a computer using recursive relations, whether you are using finite difference, finite element, etc. Next. Now consider another important problem. Consider a semiconductor quantum well with L is equal to 10 nanometer where potential Vx is 0 inside the well, which means 0 is less than x is less than equal to L, and Vx is equal to V0 is equal to 300 milli electron volt outside the well. Calculate the energy eigenvalues. Read this problem. Now, how you will solve this? You will solve this using first 1D time independent Schrodinger equation. You know what is the Schrodinger equation here. Psi, you know wave function, E is energy values, Vx is the potential next. Now what you will do is first discretize it. So take xi is equal to I delta x, I is equal to 1 to n is equal to 100. Then d square psi by dx square is this by using difference. So psi x minus xi minus 1 minus 2 psi xi plus psi xi plus 1 by delta x square. Next. Then formulate the matrix. So what you will do is put these values, that is discrete value, difference values in the differential equation. And once you put it in the differential equation, you will get this equation. Now minus h square by 2m star is into this value, the discrete values, plus bi psi xi is equal to e psi xi. Now this you can see this is in the form of a matrix. So rearrange it into three coefficient, three terms, psi xi minus 1, psi xi and psi xi plus 1. I is the grid points. Therefore, this will give you a Hamiltonian matrix of the form H psi is equal to E psi, which is a eigenvalue problem. Next. Next. So now in the H psi is equal to E psi, H is a tridiagonal matrix. Its diagonal terms HII are H cross square by M star delta X square plus BI, and off diagonal terms are minus H cross square minus plus. So this will be minus plus H cross square by 2 M star delta X square. And wave function vector psi are given. Dirichlet boundary condition you will use psi x is equal to 0, at x is equal to 0 and n. Then solution steps, put these values in your computer, construct the Hamiltonian matrix H with Vx is equal to 0 inside the well, and V0 outside the well. Then solve using Python or MATLAB, etc. In Python, you can use NumPy, linear EIG, and solve the matrix SI is equal to ESI. Once you solve this, you will get eigenvalues ESI that correspond to allowed energy levels. And energy vector psi, they give discrete value wave functions. First few eigenvalues, they represent lowest energy levels for the particle in the quantum wave. Next. Now this is the result. E1 is 40, and MEV, E2 is equal to this, E3 is equal to this. The corresponding wave functions, they will describe the probability density of the particle at these energy levels. The energy eigenvalues, they provide quantized energy levels of the particle in the well, which is crucial for understanding electron behavior in the semiconductors, quantum dots, or nanostructures. Similarly, eigenfunctions, they describe partial distribution of the electron, which helps in calculating transition probabilities, tunneling effects, designing operating devices. So you use a finite difference technique to solve similar problems, differential problems. This is another problem which is from optics. Consider a step index optical fiber with core radius 4 micrometer, core refractive index 1.5, plunging refractive index 1.48. Assume it is operating at wavelength lambda is equal to 1.55 micrometer. Next. Objective is to model light propagation in this. Next. Find out this. Now use cylindrical coordinate system. So scalar wave, find out the scalar wave equation delta square Ez plus k0 square n square Ez is equal to beta square Ez. N is refractive index, it depends on R. The k0 is this, nr is refractive index profile, beta is propagation constant. Goal is to find beta square and corresponding Ez next. Now, what you will do is, since we are considering a fiber, so we will use cylindrical coordinate system. Write the equation in the cylindrical coordinate system first. Differential equation, write it in the cylindrical coordinate system. Because it has azimuthal independence, because due to circular cross section, so dou Ez by dou phi is equal to 0. Put that equation simplifies, then open that, rearrange it, you get the bottom equation. This is a second order differential equation. The bottom second order differential equation you will get next. Now what you will do is discretize R as Ri is equal to I delta R, I is equal to 0 to n. Then use central difference for the derivatives. D square Ez by dr square, first find it out. Then 1 by r dEz by dr, that also you find out. Put it in the differential equation. So you will construct a finite difference equation which is given Ezi plus 1 minus 2Ezi plus Ezi minus 1 by delta r square plus the other term plus the Ezi term, that is equal to 0. Then you rearrange this in the form ai I minus 1 into Ez I minus 1 plus ai Ezi plus ai I plus 1 into Ez I plus 1 is equal to beta square Ez. Take it into this form. So that also you can now put it in the matrix operator equation. AE is equal to beta square E. A is a tridiagonal matrix. Main diagonal AII is minus 2 by delta R square plus K0 square N square Ri, and off diagonal matrices are this 1 by delta R square plus minus 1 by 2 Ri delta R. So for different I you will get AII and AI plus 1 or minus 1. So upper triangular matrix or lower triangular matrix. Then apply the boundary condition. Ez at r is equal to 0 is finite. So Ez0 is equal to Ez1 that you use. Ez at r is equal to capital R at the boundary, that is equal to 0. because field vanishes outside the fiber. Next. Then solve using numerical method. Use Python or MATLAB. In Python, you can use Skippy, linear algebra, eigenvalue, EIGN. It is not GH, EIGN. To solve AE plus beta, AE is equal to beta square E. Here, once you solve it, you will get beta and E. Beta square 1, beta square 2, etc. They represent the propagation constant squared for optical fiber motion. E1, E2, etc., they give the discrete electric field at each grid point for the eigenvector to ensure physical relevance. So if it is continuous, then you normalize as integration of the absolute value of Ez. But for discrete points, now since we are discretizing, it will be summation I is equal to 1 to n, absolute Ez I square Ri delta R is equal to 1. Normalize this and to get the physical relevance. Next. Now with different, oh, one parameter is missing here. Then with the physical parameters, put the physical parameters, import numpy as np in the Python. For skippy.linear algebra, import eigh. Results are these, beta 1, beta 2, field distribution are given here. Next. So here eigenvalues, they give the propagation constant beta square. They determine the allowed modes in the fiber, which affect its capacity and dispersion properties. Field distributions EZR, they provide from eigenfunction, they provide insight into mode confinement, power distribution. Next. Now what we saw? We saw that we in the solution of differential equation we are using finite difference method, and from the finite difference method we are getting a recursive relation. For finding out r sin theta, Aryabhatta used the same principle, because you know sine is d square y by d x square or d theta square plus y is equal to 0. Solve that differential equation, second order differential equation. Doing that, you can always get this. And take Bn is equal to R sine Nh, then delta n is equal to Bn plus 1 minus Bn, delta n plus 1 minus delta n is equal to minus Bn into this delta 1 minus delta 2 by B1, delta 1 minus delta 2, take it approximately equal to 1 minute by, because delta 1 is 225, delta 2 is 224, difference is 1 minute. Put that delta n plus 1 minus delta n up is approximately equal to Bn by B1. B1 is 225, that you can use. Now this will become delta n plus 1, put this value, delta n plus 1 will be and will be equal to delta n minus Bn by B1. Now Bn by B1, Bn is R sin Nh by R sin B1 is R sin H. Then delta n. Delta n is Bn plus 1 minus 1, that is R sin Nh minus R sin n minus 1h. And delta n plus 1 is R sin n plus 1h minus R sin Nh. So you get this recursive relation, which is perhaps the first recursive relation in the form of a differential or difference equation. Next. So this was first given in India. The recursion relation and finite difference was coming from Aryabhatta in India. But this does not give you the exact result. The exact exertion relation is this. R sin n plus 1 theta minus R sin theta is equal to this. Next. The same thing we can put in this form also. R sin n theta minus R sin theta, let us write it as dn. R value, theta value we know. Then dn minus 1 is equal to minus sin n minus 1 theta by sin theta. Now, if you look at this shows us something like sin theta and its differentiation minus cos theta. So sin theta differentiates sin theta cos theta. Second differentiation is minus sin theta. So that we get. So differentiation also was available in India. Next. Then comes these two problems. Object moves in a potential field where potential energy is tabulated at discrete points. Giving this is the given data. Find at V.25. Similarly, for a resistor, find the voltage at T is equal to 0 0.5 millisecond. What we do if you get tabulated data, not continuous, not no closed expression, then usually we use next Newton-Stirling interpolation formula. So this is credited to Newton and Stirling. Now let us see what was in India. This is available was given by this series was given by Brahmagupta for finding the R sign values. R sign n plus h delta is equal to bn plus this thing. If you compare this with the Stirling formula, you will find that both are exactly same. Next, you find that both are exactly same. So this interpolation formula was also available in India earlier. Next. This is an example. Let me skip this example of using the Stirling formula because you must have used Newton's Stirling formula earlier. Then we know that Newton gave the series for sine and cosine, series expansion, Taylor series expansion of sine and cosine were given by Newton. But if you look at Madhava gave two slopes. First slope gives you the sine series expansion. Second slope gives us the cosine series expansion because sine and cosine were used in astronomical calculation. Then Bhaskara he used geometrical proof of sine y dash minus sine y is equal to y dash minus y by y into cos y. He used a tangent to the circle to find the Tatkalika Bhogakhanda, which is the sign difference. So sign difference was also given by Bhaskaracharya earlier. He introduced Tulagati, Tatkalika Gati, Sukma Gati. Tatkalika Gati means the instantaneous velocity for which he has to use the concept of limit, which is, he said, that no greater than a truti. Limit goes to 0, theta goes to 0, or t delta t goes to 0, no greater than a truti. Truti is 1 by 33.750 seconds. So this measures the velocity, instantaneous velocity, taking this infinitesimal unit of time. So limit was known to India earlier. Then he was aware that a variable attains the maximum value, its differential vanishes. Wherever it has a maxima, its differentiation vanishes. So he concluded that for some uh, intermediate position at the differential of the equation of center is equal to 0, which we read in our college as the mean value theorem or Rolle's theorem. So it was much before the 1691. This was proposed by Bhaskaracharya or Bhaskar II. Finally, we come to integration. How do you find the surface area of a sphere? So why this Shoko gives us what is done there. What we do is divide the Shoko into divide the sphere into different strips. Take the upper half of the sphere, divide into different strips. Each strip width is 225 degree. Then take any strip, nth strip, then elongate it, cut it and elongate it. So that will give you a trapezium. Find out the area of the trapezium. Take all these n trapeziums, add the area of all those trapeziums. That gives us the area of the sphere, upper half of the sphere. Multiply that by 2. That gives the surface area of the sphere. That gives us the surface area of the sphere. And now what is that? How do you do it today? Today, when you integrate, integration is continuous summation. So you usually do the same thing. So that is what is done here. AN is the area of the nth trapezium. We have found out its B are the tabulated R sign values that we have discussed earlier. Then surface area is 2 into C by R. C is circumference, R is radius. So C by R circumference by R is pi. So that is 2 pi, 2 pi R. Okay. So with that, we'll conclude for today, and I am open to uh, comments or questions.
Thank you, sir. Now the talk is open for discussion. Anyone would like to ask any question? Professor Misra will be very happy to answer. I have unmuted all. So you can just respond or you can ask your question or put in the chat box. Anything you would like to ask, sir will be very happy to answer. Sir, I have some issue in my chat box, so I cannot open that.
No,
So,
I can see the chat box.
yeah. I have unmuted all, so you can ask if you have any queries.
I think sometimes this video or audio was acha. Okay, this was for 130p. There is nothing in the chat box.
Okay. Yes, sir. If there are no more questions, so sir, thank you very much for
Thank you, Satya.
sharing your expertise and enlightening our participants. Thank you very much, sir, joining with us.
Thank you. So I'll leave now.
Yes, sir. Yes, sir.
Okay, thanks.